Section 4.7, optimization. Let me tell you what's going on. All right, we're going to go to the first problem that we have. This is called the maximum volume of a square pizza box with a side of 18 inches. So let me draw a picture here real quick and kind of explain what we're doing. The side of your pizza box is 18 inches. Okay, and what you're going to do is something that I remember doing in art class when I was in elementary school. Your art teacher told you to cut out these little squares and made them all the same dimension. Okay, and when you cut these out and these disappeared, right, then your teacher would tell you along this edge here, okay, you would fold in these inside pieces so that you would get what looked like a box. Okay, and these edges that you would, well, first of all, those would go away. Okay, and the edges that you would fold up, okay, would actually turn out to be this edge that you'd have right here. And so this would fold up. This would fold up. And so this one, this is in the back, you can't see it, and same thing there. All right. Now this distance, okay, that you were cutting out turns out to be the same as the height. Okay, so all these heights are x, right? And these new edges, which are kind of determined based off the amount of x that you cut out, okay? Okay, those squares that you come out, they change. Okay, so the larger the square that you cut out, the smaller the side will be because you have less distance remaining, if that makes sense. So here's what I do. I got to figure out what is that respective length. Okay, and here's what I know. I know I start with 18, and if I subtract out an x here and an x here, okay, you're subtracting out basically two x's. Okay, so I have 18 minus 2x for one respective length. And the other one is also 18 minus 2x. Okay, and so when you think about the volume, okay, of your respective box here, and understand this is a box without a top, okay, but still a box. Here's what you got. You got volume is equal to length times width times height. And your length, okay, is 18 minus 2x, as is your width, and your height is x. Okay, and so since they're all with respect to x, and your volumes will change with respect to whatever this height is, okay, the height that you decide to basically cut out in terms of the area of that x, or that little square, gives you this formula, 18 minus 2x squared times x. Okay. And here's what I'm going to do. Think about what we've been talking about this chapter. We're going to find a maximum, okay? And a maximum is found based off our function when we have derivatives that are set equal to 0 as our minimums, okay? So let's think first about what our domain can be, all right? So we don't have a complete real number system with respect to x because this is a measurement, okay? And if I'm looking at a small distance, we know that my lowest value that it'll approach is 0. Can't really have a height of 0, otherwise you don't really have a box, you just have a flat piece of cardboard. And if I think hard about the height that this could, sorry, the max that this could be, well, here's kind of our hint. If this is 18, as I shared on the other side, and I keep cutting out bigger and bigger pieces on each side, okay, the biggest square that I could cut out would have a side of 9, because it would be 9 here and 9 there. And if you did that, you would basically have the highest height that you could possibly have, but then you would have no edge along the length and the width. okay? Because basically this whole square would cancel out and you have no sides remaining, okay? And so I know that it has to approach 9. You can't really ever hit 9 because once you hit 9, the box kind of dissolves away, okay? So here's what I'm going to do. My equation, v of x equals 18 minus 2x squared times x. Now, sometimes I'll do this. I'll say, I'm just going to go take a derivative, and I know how to do that. That's a product rule. But I think it may be to our advantage, and that's not a times sign. F of x, sorry, v of x. I'm going to actually FOIL this out. I'm going to multiply this out. Okay, and so I'm going to leave the x out here just to start with, and I'm going to multiply 18 minus 2x by itself, and that's going to give me 324 minus 72x plus 4x squared. All right, and then further, if I distribute that x through, I have 324x minus 72x squared plus 4x cubed. Okay, and I haven't really done any calculus yet because I haven't taken the derivative. I've just cleaned this up to make it look a little bit more manageable so that when I take a derivative, it's a little bit easier, at least in my opinion. Okay, so the derivative of 324x is just 324. Derivative of negative 72x squared is negative 144x. And the derivative of this last term is 12x squared. Okay. Now I'm going to do two things. First, remember again that to find a maximum or a minimum, we take the derivative and we set it equal to 0. So I did that. I took the derivative. I'm going to set it equal to 0. Okay. And I'm going to do two things. First, I'm going to put it in descending order by power because I think it's look a little bit nicer. And then the second thing I'm going to do is I'm going to try to reduce this a little bit. Okay. And in this case, it means I'm going to divide everything by 12. Okay, so I'm going to put the 12x squared first, but only after I divide by 12, and that'll leave me with an x squared. Sorry, that's 144x. I'll take the 144x and divide by 12, and that'll give me 12x. And 324 divided by 12 is 27. Okay. And some people say, hey, can I take this and just put it in my calculator, graph it, and find the roots, the 0? And you could, certainly. But I just think it's easier sometimes to not use your calculator if things factor. And in this case, they do. Two numbers that multiply to give you a positive 27 and add to give you negative 12 are 9 and 3. Okay, so I'll solve and we'll set each one equal to 0. And we got 9 and 3. And remember, these are the two numbers that could represent this value for x for a dimension, but 9 will not count. Okay, and the reason why is because if you made a side of 9 for your height, then you would have sides of 0 for both your length and your width. So that will go away. Sometimes I like to verify that this is going to provide an absolute max for us. And so just to verify, there's x, there's f prime of x. I know that when I input 3, actually I made that an f, let me call that a v, sorry. I'll get a 0. All right, and I'll pick a number smaller than that and a number bigger than that. So there's a 1, there's a 4. You can plug it into any one of these. Since I didn't divide by a negative, okay, we're good for this one or this one or this one. If I plug in 1 here, I will get negative 8 times 1 and minus 3 is negative 2. That gives you 16. And if you plug in 4, you get negative 5. 4 minus 3 is 1. That gives you negative 5. Okay, and what this means is that we do have a maximum. Okay, and in this case, I could plug in 0 and 9, but again, those are my boundaries for my domain. It's not a closed interval because, again, those would give me values of 0, or yeah, for our volume. But in this case, it will be an absolute max. Will be at x equals 3. Okay, because v prime of x moves from positive to negative values at x equals 3. All right, so again, notice I use the word values. Okay, positive values and negative values, those changed at x equals 3. Okay, so good. We know it's a max and not a min. We had to verify that. And again, find the volume. So volume is length times width times height. And so that's 18 minus 2x, 18 minus 2x times x. And I suppose I could write this with respect to x. Okay, so when I plug in 3, 18 minus 2 times 3, 18 minus 2 times 3 times 3. Okay, and once you plug this in, you don't really have to show the work. You can just finish it out. And actually, if this is free response, you could stop there. Because remember that in free response questions, you don't have to simplify your math. Okay. Nevertheless, I know some of you are curious. That gives you 12. This gives you 12. This gives you 3. And that is 432. I didn't put my units in just because sometimes I don't like writing that with my tablet, but that is inches cubed. Okay. All righty. Let's move on to the second one. And remember, if you get stuck or if you want to look back at this work, it's okay to pause this video, work backwards, look at and see what we did, and then you know, go through it and check it and make sure that the work that we provided is correct, okay, and that it makes sense. And if not, take a look at it, ask me a question. You can certainly do that. All right, infinite goat problem. This comes to a story that I talked about in class where I almost won a goat in a raffle. Right, and I'm thinking about my house, which was right here, and my backyard, which is this little rectangle backyard. And here's the deal. I had a backyard that I could have put this goat in, but I also had 2 crazy chihuahuas that would probably have driven this goat nuts. All right, and so I had this 100 feet of fence that I was going to put this goat in, okay? And it was going to be rectangular. So let me talk about that too. Okay, 100 feet of rectangular fence. And what I want to know is, what is the maximum area for the fence? What's the maximum area that can be created by the fence? Okay, now here's the deal. The way I constructed my backyard was this way. I said it was rectangular, okay, and you can kind of see that outlined here. And I put it up against a brick wall that currently existed as the border of my fence. So I didn't need to make a fence side on this right-hand side. Okay, so properties of a rectangular say this. I remember this back in geometry. Opposite sides of a rectangle are the same, so same distance. So if that's an x, then so is this guy. And I can make this a y. I don't know if the adjacent sides are the same. They could be, but we're not really sure if that's going to provide the maximum. Okay. And this side here, I'm not going to put a y here because I don't have real fence on that side. I just have brick wall. Okay, and I didn't need that fourth side to represent part of my fence, and I'll be able to save a little bit of money, you know, and actually create a little bit bigger area for this goat, so it's not being attacked by my chihuahuas. So I'll give it little horns here. And there's my chihuahuas. Okay, so how am I going to go about doing this? Well, when I think about this problem, I have two basic areas that come to mind, sorry, two basic formulas that come to mind with respect to a rectangle. One, of course, is the area. Okay, I'll write that over here. Area is equal to length times width. Okay. And the other one is perimeter with respect to this rectangle. Now, this rectangle doesn't have 4 sides with respect to fencing. It only has 3 sides. So I'm going to write that x plus y plus x. All right, and I've got 2x plus y is equal to perimeter. All right, and so my perimeter is 100. Okay, they give that to us. Okay, and area is length times width. So what is the length and width of my, oops, the length and the width are represented in this case by x and y. So I'll write that. And since I'm trying to find a maximum area, that means I would take this area formula and derive it, okay? And then set it equal to 0, which is what we typically do for finding maximums. Now, before I do that, okay, I want to have this right side here represented in terms of one variable. I would either want it in x's or in y's, right? And you're like, well, how would you do that? And there is a way, and the only way that you can do that is by considering another formula that may be used in this problem and using it for substitution. All right, so when you consider 100 equals 2x plus y, I can easily solve for one of these variables, the x or the y, and then input it into my area formula. And what may be the easier area dimension to solve for? The length or the width, or the x or the y? Probably the y. Okay, because, well, the 100 would stay there, and the minus 2x would travel over, and then I can substitute it in. Okay, so my x would be there, y is replaced with 100 minus 2x, and notice that behind here, this is not a time sign, that's just a representation of a function, and so I'll say a of x is equal to x times 100 minus 2x. Okay, and so you can figure out the maximum area based off the dimension of this side here of x. As it gets smaller, it'll give you a different area. As it gets larger, it gives you another different area. We got to figure out what value of x will give us the maximum area between this x and this y. So now, to do that, of course, we'll take the derivative, but again, it may be wise to distribute first. So this is 100x minus 2x squared. And then if I want to take the derivative of 100x is 100, and that'll be minus 2 times 2 is 4 power rule x to the first. We'll set this equal to 0. And if I add the 4x to both sides and divide, I get 25. Okay. Now that's just this side. There's 25 here, 25 here. And what I need is the y now. Okay, well, how do I find y? Well, y is already listed. So if I do 100 minus 2 times that x, which is 25, okay, that's 100 minus 50, which is 50. All right, so the dimensions for my maximum area we said was length times width, or x times y. And so it is 25 times 50. Now let's do this first. I actually found the y, but let's make sure that this is a max. I'm sorry, I shortchanged this. Okay, so this is x. Let's make this a prime of x. And I didn't mean to shortcut this. When you get 25, plug it into the derivative right here, you will get 0. But let's just put some numbers in below it and above it. So I'll just pick 24 and 26 and 24. If I plug that into this x, okay, which is my derivative, okay, I'm going to get 90, I'm going to get 4. Okay. And if you plug in 26, it's actually going to give you something a little bit bigger in the back. And when you subtract that from 100, you get negative 4. And so, yes, this is going to be a max. So at x equals 25, okay, it is a max. And it's not just a max, it's the absolute max. And maybe we know that because this is a parabola. We know it goes upside down because of the negative sign in front of the x squared. And so definitely a max has to exist, and it would be an absolute. And it's an absolute max because we'll say that for a prime of x moves from positive to negative numbers at x equals 25. Okay, so again, we're addressing a prime of x, okay, and we're just saying that you're moving from positive values to negative values. Remember, a prime of x, that's like your slope function, okay, moving from positive slopes to negative slopes, okay. But what we'll do is we'll say for a prime of x, these are actually positive values to negative values at x equals 25, okay. All right, and then finally, if we multiply those together, you get 1250 feet cubed. There you go. Sorry, that one a little fast, but that's the maximum area which they asked. All right, keeping on going. I've got 5 of these, so we're on number 3. It says the product of 2 positive numbers is 100 and 185. Okay, find the sum that is a minimum. Okay, well, let's think about this. Let's do this. 2 numbers, so I don't know. Let's try the first number. Let's identify that. The first number is equal to x, and the second number will be equal to y. And it says the products must be equal to 185. Okay. It says find the sum that is the minimum. Okay, so sum function, and all you're doing is, it sounds almost too simple, it's just adding these. Okay, and we need a function that will make this a minimum. Now, I am not allowed to derive this yet. If I can, I want to substitute something in for x or something in for y in terms of the other variable. Okay, so since this is kind of solid, and I know what that is, I'm going to divide both sides by x. Okay, and then with that, I can take this guy and substitute it in for that y. Okay. All right, so now I have a function in terms of x that's represented by this formula that will help us determine a sum, okay, that adds up to 185. Sorry, product that multiplies to 185, but it's in the form of a sum. Okay. All right, so like before, we'll take a derivative. Derivative of x is 1. Now, think about this. This is really 185x to the negative 1. Okay, and so if I move the negative 1 to the outside, that now becomes negative 185x to the negative 2 once you derive it. Okay. And if I set this equal to 0, okay, I get this. Let me put the x squared on the bottom. and then add this over. And if I multiply both sides by x squared, I get this. And then x is equal to plus or minus the square root of 185. Now, ask yourself, like, dang, I don't think 185 square roots nicely. It doesn't, okay? But that's okay. It just says two positive numbers, okay? And so that means I really don't even need this negative. In this case, all I need is 185 square rooted. And I'm not going to even square root it because it doesn't work out cleanly, and it doesn't, this is really the most exact answer. Okay. All right, now what would my other number be? Well, if I did the y is equal to 185. I'm looking right up here. Okay. Divided by x, and again is the square root of 185. And that turns out to be the square root of 185. Okay, so this is your x, this is your y. I'm going to verify in a second that it is a potential minimum in just a second, but let me kind of answer the question here. The sum is, well, it's your x, which is 185 square rooted, plus the y, which is also the square root of 185. And together, okay, there's two of them. So it's 2 times the square root of 185. Okay, that is the sum. Okay, now let's just verify that this is a minimum. Here is x. Here is s prime of x as we've written it right here and right here and right there. And so here's the square root of 185. I know that will give me 0. Okay. Since they have to be positive, I can just pick any number that's smaller than it. And I'm going to pick one that is kind of easy. I'm just going to pick 1. Okay. It has to be bigger than 0 because it's positive, but it has to be less than the square root of 185. 1 looks good to me. If I plug in 1 for x, I'm going to get 1 minus 185 over 1 squared. And that gives me negative 184. Okay. And if I pick something bigger than the square root of 185, I'm just going to say 15. You're like, why 15? Just because I know that the square root of 85 is 185, excuse me, it's less than 15. 15 is the same as the square root of 225, and that's a little bit bigger. So when I do that, I get 1 minus 185 over 15 squared, which is 225, and 1 minus 185. I don't know how that got that way. Sorry. $225. That looks like the same thing. So let me do this. Sorry to make this longer than what it should be. I'm just rewriting some things, so I'll make this better. Let's write 1 as 225 over 225. And that leaves me with 225 on the bottom. And on the top, if I subtract those, 15 and 25 give me 40. And really the bottom line is that this is a positive and this is a negative. So what I know is that the square root of 185 is a minimum. And is a relative minimum. And it actually will probably be our maximum, sorry, our absolute minimum. But what we'll say is because for s prime of x, okay, we move, let's say moves from negative to positive values at x equals the square root of 185. Wow, sorry, that was too fast. But we are good. All right, so that's the verification that it is a minimum, because we go from negative values to positive values for our s prime of x at the square root of 185. Okay, plug those in. We're good. All right, we are down to 2 more of these. Okay, you can see how highly involved they are. However, the process is the same from here down every single time. All you do is you take your equation that you make, your function that you make, take the derivative, set it equal to 0, verify that it's a max or a min, then input your value back into the original. Okay, it was the same thing on the one before that. Okay, here's your function, take the derivative, set it equal to 0, verify it's either a max or a min,